So again, we were using the definition of the derivative, which was the limit as h goes to 0. You plug in x plus h. So here I would have 2x plus h cubed plus 4x plus h minus f of x all over h. This will be another one that we can figure out how much time it takes us to do this. And later we'll be able to do this one in under 5 seconds. We're going to try to get up to page 19. So we are on page 14. But there's only one example per page and then just some talking stuff. So what would take a long time in this one right now? You would have to actually expand x plus h cubed. You could either use Pascal's triangle, do it by hand, but x plus h cubed is x cubed plus 3x squared h plus 3x h squared plus h cubed.
I'm just going to memorize that.
And then we still have the plus 4 h, and then minus this, which if I distribute the negative, all over h. This too is going to get distributed to each of those terms. And when it does, do you see that this will simplify with that? And this one right here simplifies with that. What's going to happen in a lot of our questions is all the terms without h's will cancel out. Then if all the remaining terms have h's, you can factor that h out, which allows you to do this, which is what our whole goal in a limit is. Can we get rid of the thing that's causing us a problem? The non-permissible value. Once you get rid of the thing that's causing the problem, you can plug in 0 for h and see what you would have left. And the only things that would be left would be the 6x squared and the plus 4. What was annoying in this one was that exponent of 3, right? That exponent of 3 made you have to do the x plus h to the exponent of 3 and expand it. Later on we're going to do bigger exponents like 75. Oh. Expanding the 75 would be insane here. So we're definitely going to develop a shortcut. And the shortcut will mean you can go directly from the question right to the answer in a matter of seconds.
Graphing calculator method.
No, this is by hand. Like, you just look at it and you'll just know. Okay? But we haven't learned the shortcut rules yet, so we have to use the long cuts. I don't know if that's the word. They're shortcuts, are the other ones long cuts?
The scenic route.
The scenic route, where you can see all the numbers as you're going along. Okay. So how do we use the definition of the derivative? First we plug in x plus h. So on the top you'd have x plus h plus 2. And on the bottom you'd have 2x plus h, which I already distributed the 2. Are you okay with that? 2x plus 2h minus 1. Minus the original all over h. And now we have to use our algebra skills to get the top as a single fraction. And we got to hope that we can cancel out that h in the end. So what would that look like? Well, if I'm subtracting fractions, I need a common denominator, even though those denominators are not very pretty. First one I'd have to multiply by 2x minus 1 and 2x minus 1. The second one by 2x plus 2h minus 1, 2x plus 2h minus 1. Once I get that common denominator, and I'm subtracting, really important, you're subtracting all of this, so I added those extra brackets there to remind us that this negative is going to get distributed to each one. And when it gets distributed to each one, I hope you can see that the 2x squared and the minus 2x squared will go away. The minus x and the minus a minus x plus x, those would go away. The 4x and minus 4x go away. I'm running out of fun colors. And the minus 2 minus the minus 2 would go away. If things work out nicely, everything without h's goes away. Yes, now you can't see what's underneath the things that I struck out?
Can you zoom in a little bit?
Yeah, I can do that.
I can't see.
That's your fault for randomly being put at the back.
Maxwell needs to lock in.
Although if we check the seating plan, is that your spot?
No.
No. Oh! Ooh. So what do we get? We just get the minus 5h. We have another thing I can cancel out. I'll get another color. Red. The 2xh here cancels out with this 2xh. The only thing that's left is minus 5h's. This is in your denominator. If you multiply now by the reciprocal, because I can think of this h, the bottom of my fraction is the fraction h over 1. How do you divide by fractions? You multiply by the reciprocal. And then wonderfully, those h's cancel out. Again, all this writing, this one's a longer question. Like the other ones I said you could do it under 5 seconds. This one might take 12 to 15 seconds. But compared to this, you're going to be like, why did you ever put us through this torture? Well, this is how it began. This is how the ideas began. And then mathematicians proved shortcuts, which was like, thank you for proving a shortcut, because now you can use the shortcut every single time. Is it all right if I zoom back out? Yes? Everybody good? determining if a derivative exists. So, how do we know if a limit exists? The left side limit and the right side limit have to be exactly the same. And here we get the very informal definition of when a derivative exists. It's continuous and it's smooth. If you went to go touch the curve, you wouldn't cut your finger. Absolute values have like a super sharp point on them. If you touch that point, it'll prick your finger and your finger will bleed because it's so pointy. We would say the derivative does not exist on an absolute value graph at that one point because it's, ouch, super pointy. But any graph that's smooth, like a sine curve, oh, it's so rounded and smooth. That's what we mean by smooth, nice and round. Parabolas are round. X-cube graphs are round, they're not pointy. If it's continuous and it's smooth, then the left limit and the right limit will exist. And the derivative will exist. Think about an absolute value. Wow, this is green. We can think about it even if it's green. Can you see that on this side, your slope is 1, and on this side, your slope is -1? So as I go to the sharp, prickly point, from the left side, my slopes are -1. From the right side, my slopes are 1. So we would say, since the left limit and the right limit are two different things, the limit at that sharp point does not exist, and the derivative would not exist. So we need our graph to be smooth and continuous. You know those questions that they have a piecewise graph and you had to determine A and B for it to be continuous? They'll have on your exam, we need it to be differentiable. So you have to prove it's continuous and you have to prove that you wouldn't cut your finger at those points and it's smooth. Oh. So here, we just did this one. Sharp points we call corners. So the absolute value graph has a sharp point, it has a corner, it does not exist at that place. So a corner is where the left side limit and the right side limit exist. We can find those at 1 and -1, but they're not equal. The derivative does not exist at cusps. Here's a new mathematical word for you. Here's the graph of x to the 2/3. You've never graphed x to the 2/3 before. It has a sharp point. You cut your finger if you touch that spot. But unlike the absolute value, when you look at both of these, the slopes become straight lines almost because it gets super up and down. And we would say both of them have infinite slopes. But it's infinity on one side, negative infinity on the other. And those are called cusps. You have places where a tangent can be drawn, but the tangent is vertical. Here's the cube root of x graph, which is the inverse of x cubed graph, with a shift. I've shifted it over 2 to the right. And I flipped it. Whatever, doesn't matter. Like a cube root graph. If you have a vertical asymptote, it's not sharp there. But that is an example of where another place it does not exist. So here's where the smooth and continuous is like a mostly good rule. But this graph is smooth and it is continuous, but it still has a place where the derivative doesn't exist. So the smooth and continuous idea is mostly right, but there's sometimes that you can have vertical tangents where the derivative doesn't exist. And number 4, if you have a discontinuity, the graph for sure isn't smooth and continuous. So this is obvious that the derivative will not exist at that point. In fact, the derivative, any graph that just ends at a point, you cannot draw a tangent to a single point because it's like, should I draw the tangent like this, or touching only like that, or touching only like that? There's so many possibilities. Plus, if you touch the end of that, it would hurt your finger.
The dot?
I know, it's a really sharp dot. They don't call it a point for nothing. So if f of x is the absolute value of x plus 3, how would we show that it's not differentiable at x equals negative 3? Well, if we went from the limit from the left, okay? And here you could, I'm using one of my slope formulas at the specific point. F of x minus f of c over x minus c. I simplify it and I get x plus 3 in absolute values over x plus 3. But the bottom, because you're coming from the left, is a small negative number. The top is a small positive number. They've got to be the same number. So they'll always equal 1. But because 1 is positive and 1 is negative, you get negative 1. On the other side, you do the same thing. But this time they'd both be small positive numbers. So you get positive 1. And you make a statement that since the left-hand limit is not equal to the right-hand limit, it is not differentiable at x equals minus 3. And again, which tangent formula was I using? I was using that tangent formula, the limit as x goes to a value of f of x minus, that is supposed to be c, f of c. So here we have a piecewise function. And if you check each of these, when you plug in 1, right, 3 minus 2 is 1, 1 squared is 1. If we draw the graph of this, it kind of looks like this. It looks like a parabola, but technically, when x is greater than or equal to 1, this is just, this part here in green is a perfectly straight line. This part in purple is your nice parabola. It looks, well, it is continuous. That part's for sure. The question is, at this red dot there, is it sharp enough that if I touched it, it would cause my finger to bleed? Or is it smooth? Ooh. Let's find out. As we go from 1 from the minus side. You would get x minus 1, x plus 1, the top would factor. These would cancel out, and 1 plus 1 would be 2. If you go from 1 from the plus side, which would be on the 3x minus 2 graph, the little red dot was foreboding. I touched it, I would cut my finger and create blood. Because here, the slope is 3. Those slopes are not the same. So it is continuous, but it is not differentiable. So do you know what the exam does? The exam says instead of 3x minus 2, they write ax plus b. There is one line that you could put there that would work and make it smooth at that point, so you wouldn't cut your finger. What line would that be? Well, I'm not going to solve that completely right now. I'm just going to give you the idea. First of all, it would have to be continuous. So does it make sense that when you plug in 1, it would have to equal 1? Next, what do we need the slope to equal? We already figured out from the left that the slope needs to be 2. So in this one, you know that a would also need to be 2. So what's the only answer that works? If a is 2, well, I am solving this. I'm sorry. I plug in 2 for a and move it over. B is minus 1. So if they had given us 2x minus 1, it would be smooth and continuous. But 3x minus 2 creates that red dot when you touch it there, because your finger would, there'd be like, it's very deceiving, but there's a tiny little sharp point there. You're just running your finger along and then, ow! You start to bleed. I start seeing in this unit, students are going to come, I'm wearing gloves for these questions, in case there's any sharp points. So to end, a theorem. If a function is differentiable at any point A, it must be continuous. It's kind of the flip, right? If it's smooth and continuous, it's differentiable. So if we know it's differentiable, it must be smooth and continuous. Differentiability implies continuity, but continuity does not imply differentiability. Ooh. So just because something's continuous, it could have one of those sharp points.
Can Jonathan Decina